This video is a step-by-step solution for the example entitled Using the Energy Balance and Ideal Gas Tables. In this example, you will learn about applying the energy balance for a closed system at steady state undergoing a compression and to evaluate the work in the presence of a known heat transfer. Let's look at the problem statement as given to us. A piston cylinder assembly contains 2 pounds of air at a temperature of 540 degrees Rankine and a pressure of 1 atmosphere. The air is compressed to a state where the temperature is 840 degrees Rankine and the pressure is 6 atmospheres. During the compression, there is a heat transfer from the air to the surroundings equal to 20 BTU. Using the ideal gas model for air, determine the work during the process in BTU. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. For the given information, here highlighted in red, we have the following. A piston cylinder assembly contains 2 pounds of air at a temperature of 540 degrees Rankine and a pressure of 1 atmosphere. The air is compressed to a state where the temperature is 840 degrees Rankine and the pressure is 6 atmosphere. During the compression, there is a heat transfer from the air to the surrounding equal to 20 BTU. Use the ideal gas model for air. And highlighted in green, the information to be found. Determine the work during the process in BTU. Let's start develop the solution. The first thing to do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in a critical read of the problem statement presented here in a bulleted list format. 2 pounds of air are compressed between two specified states while there is a heat transfer from the air of a known amount. The next thing to do is to summarize what we have to find. This is again the information we highlighted in green in a critical read of the problem statement, presented again as a bulleted list. Determine the work in BTU. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few important pieces of information that we were provided, which will help in developing a solution. The first thing to notice is that there is no mass entering or leaving the piston cylinder assembly. This immediately suggests that a closed system approach is the proper one. Having recognized this key fact, let's select our system boundary. In our case, it is selected to enclose the air and follow the physical boundary of the piston cylinder assembly as delineated on the schematic with the red dashed line. It also ties in the information provided, namely the mass of the air. The next step is to develop an appropriate thermodynamic diagram to represent the process, in this case the PV diagram as shown here. Let's highlight the relevant information provided on the diagram, namely the initial pressure and temperature at state 1, the compression process from state 1 to state 2, and the final pressure and temperature at state 2. The next step is to develop an engineering model, which is a set of simplifying assumptions which will allow to perform the analysis of the problem. The air is a closed system. The initial and final states are equilibrium states. There is no change in kinetic and potential energy. The air is modeled as an ideal gas, and the piston is the only work mode. Having completed all the required initial steps for a solution, let's develop the analysis. An energy balance for the closed system gives us delta KE plus delta PE plus delta U is equal to Q minus W. In this expression, the kinetic and potential energy terms vanish by assumption 2. Dropping the negligible terms and solving for W, we obtain W is equal to Q minus delta U, or W is equal to Q minus M times U2 minus U1. From the problem statement, the heat transfer during the process is given as Q is equal to minus 20 BTU. Finally, we need to evaluate the internal energy at state 1 and 2. From the table of ideal gas properties of air in English units, we get the following values. At T1 equal 540 degrees Rankine, U1 is equal to 92.04 BTU per pound, and at T2 equal to 840 degrees Rankine, U2 is equal to 143.98 BTU per pound. Substituting the various numerical values, we can get the value of the work as follows. W equal minus 20 BTU minus 2 pound times 143.98 minus 92.04 BTU per pound, giving us a value W equal minus 123.9 BTU for the work. This is the answer we were seeking. Note that the minus sign indicates that work is done on the system in the process, consistent with the compression of a gas requiring work to be supplied to the system. In closing, I would like to make a few remarks. Although the initial and final states are assumed to be equilibrium states, the intervening states are not necessarily equilibrium states. So the process has been indicated on the accompanying PV diagram by a dashed line. This dashed line does not define a specific path for the process, just the initial and final states. In principle, the work could be evaluated from W is equal to the integral of PdV, but because the variation of pressure at the piston face with volume is not known during the process, as mentioned above, the integration cannot be performed without any more information about the details of the process. We can validate the assumption that the air behaves as an ideal gas between the two states as follows. From the table of atomic and molecular weights and critical properties of selected elements and compounds in English units, we get values of the critical pressure and temperature for air of Pc is equal to 37.2 and Tc is equal to 239 degrees Rankine. Therefore, at state 1, the reduced pressure and temperature are equal to PR1 is equal to 0.03 and TR1 is equal to 2.26. Similarly, at state 2, PR2 is equal to 0.16 and TR2 is equal to 3.51. By referring to the generalized compressibility chart for PR less or equal to 1, we conclude that at these states, Z is approximately equal to 1. Hence, the ideal gas law assumed in the solution is valid. Quick quiz. Replacing air by carbon dioxide by keeping all other problem statement details the same, evaluate the work in BTU. You may want to pause the video at this point to answer the question. The answer is W is equal to 125.1 BTU. Hopefully, this is what you obtained. If not, please check your work and review all the steps in this video. If still not correct, look at the following hints. You can resolve the problem using the internal energy values of carbon dioxide instead of air to evaluate the work, or you can note that the work W is equal to Q minus M times U2 minus U1 is approximately Q minus M times CV times T2 minus T1, and evaluate the work in this fashion. Also, note that the CVs of air and carbon dioxide differ only by 1% approximately over the temperature range of interest. Hence, you do not expect a large change in the magnitude of the work between air and carbon dioxide, 123.9 versus 125.1 as calculated. In closing, in this example, we have learned about applying the energy balance for a closed system at steady state undergoing compression to evaluate the work in the presence of a known heat transfer. We have also learned how to validate the given assumption that the air behaved as an ideal gas during the process. The validity of this answer is of course dependent on the specific values of the pressure and temperature encountered in the process. This concludes the step-by-step solution of the example entitled Using the Energy Balance and Ideal Gas Tables.